On the morning of September 15th, 2017, at 7:55 a.m. Pacific time, Earth received a transmission from a spacecraft that had already ceased to exist. 83 minutes earlier, Cassini had disintegrated within Saturn's atmosphere, ripped apart by friction while traveling faster than 70,000 miles per hour. Its cameras, antennas, and two-decade-old frame had turned to vapor above a world 900 million miles away. And yet the signal kept arriving. For 83 minutes, a spacecraft that no longer existed was still talking to us, and no one on Earth realized it was already gone. That detail alone is worth sitting with, because it's central to everything that follows. Right now, in 2025 and 2026, researchers are returning to Cassini's final transmissions, the last images and instrument readings it ever captured, and uncovering things so unexpected that whole areas of science are being rewritten as a result. This isn't a nostalgic look back. These are new, peer-reviewed papers appearing in journals like Nature Astronomy and the Planetary Science Journal, containing findings that are reshaping how we think about the possibility of life beyond Earth. It all leads back to those last frantic weeks, when a dying probe ventured somewhere no spacecraft had ever gone before. Keep reading, because what Cassini recorded in its final moments is only now starting to be understood. And once you know what's buried in that archive, Saturn will never look the same to you again. Among its discoveries, geysers of water erupting from the south pole of a small icy moon named Enceladus. The chemical signatures of life's basic building blocks inside those very geysers. The most detailed map ever made of Saturn's magnetic field. And in its closing act, something almost no one anticipated. By early 2017, with its fuel nearly exhausted, NASA faced a choice. Let Cassini drift and risk an eventual uncontrolled crash into Enceladus or Titan, potentially contaminating a moon that might harbor life, or take deliberate control of its ending and turn the spacecraft's final months into the boldest science campaign of the whole mission. They chose the latter, and the results were extraordinary. Starting in April 2017, Cassini was guided into territory no spacecraft had ever explored, the narrow 1/500-mile gap separating the top of Saturn's atmosphere from the inner edge of its rings. But what Cassini measured during its final passes was on an entirely different scale. Hydrocarbons and organic compounds falling at a rate as high as 10 tons per second. That figure forced scientists to completely redo their estimates of how much longer Saturn's rings can last. Based on that measured rate, the rings could disappear entirely within roughly the next 100 million years, a mere instant on planetary timescales. One of the solar system's most iconic features, which has captivated public imagination for 400 years, may turn out to be temporary, and Cassini's death dive gave us the first hard numbers proving it. But the ring reign was just the start. During those same closing orbits, Cassini's magnetometer picked up something physicists are still debating. Every other planet with a magnetic field has one that's noticeably tilted relative to its axis of rotation, Earth's. Magnetic pole is offset from true north Jupiter's field tilts about 10 degrees, and Neptune's and Uranus's are tilted so severely their magnetic poles sit nowhere near their geographic ones. By the standard theory of how planetary magnetic fields form deep within a rotating convecting core. Saturn should follow the same pattern. Instead, Cassini's closest measurements confirmed Saturn's field is aligned with its rotation axis to within 1/10 of a degree, something conventional dynamo theory says shouldn't be possible, since a field with essentially no tilt shouldn't be able to sustain itself over geological time. Interestingly, the ring reign phenomenon had actually been proposed decades before Cassini confirmed it. Ground-based telescopes in the 1980s had picked up strange patterns in Saturn's upper atmosphere dark bands and odd shifts in ionospheric density that some researchers suspected were caused by material falling from the rings along magnetic field lines. For 30 years, it stayed a hypothesis nearly impossible to verify without a spacecraft actually present. In that gap, Cassini's grand finale orbits finally delivered the direct measurements needed to confirm it, and the scale 10 tons of material every second was far larger than anyone had predicted. It's less a trickle than a waterfall, and it forced scientists to reconsider not just how long the rings will survive, but how they formed in the first place. Some now question whether Saturn's rings are ancient remnants from the solar system's earliest days, or a much younger structure born from a shattered moon or comet only a few hundred million years ago. When researchers finished combing through that data, they found roughly 155 particles carrying a chemical signature that matched Saturn's rings, precisely low in iron, unlike anything else nearby in the Saturn system. What was strange was where they turned up as far as 3 times Saturn's radius above and below the ring plane, well outside the thin, flat structure visible in every photograph ever taken of the planet. These grains are apparently being scattered into a sphere-shaped cloud of dust knocked loose by micrometeoroid impacts that vaporize tiny amounts of material before it recondenses into nanoscale grains. This halo is entirely invisible to telescopes. The only way to detect it is by flying a spacecraft straight through it and sampling directly. Researchers believe the halo forms when micrometeoroids strike the main rings at extreme speed, vaporizing small amounts of material on contact. That vapor briefly becomes a superheated plasma cloud, which cools and recondenses into nanometer-sized grains, some of which are launched outward and upward with enough force to escape the ring plane and settle into the wider halo. Cassini detected most of the vaporized material eventually falls back into the rings or into Saturn's atmosphere, but a measurable portion escapes every time this process occurs. Saturn's rings, already the most photographed structure in the solar system, turn out to be larger, messier, and stranger than any picture has ever shown. And we only know this because Cassini flew close enough during its final dive to capture the evidence. None of that compares, though, to what turned up when scientists revisited the Enceladus data, the discovery that transformed the entire conversation about life beyond Earth, and it didn't come from the farewell images of September 2017 at all. It came from something even more surprising. A flyby that had taken place 9 years earlier in 2008, sitting quietly in the archive, the whole time waiting for instruments and analytical methods that didn't yet exist. Enceladus is tiny, barely 500 kilometers across, small enough to fit inside a mid-sized country and covered in ice, so reflective, it bounces back nearly all the sunlight that hits it. When Cassini first reached Saturn in 2004, no one thought much of Enceladus. That changed almost right away. By 2005, Cassini had spotted massive geysers erupting from cracks near the moons, South Pole blasting water vapor and ice particles thousands of kilometers into space and feeding Saturn's faint E-ring. Those plumes signaled that liquid water had to exist beneath the ice, an entire hidden ocean kept from freezing by the gravitational flexing Saturn exerts on the small moon. Over the following decade, Cassini repeatedly flew through those plumes, sampling their contents. It found salts. It found silica grains that can only form through hydrothermal activity, hot water interacting with rock on an ocean floor. It found simple organic molecules. Each finding was significant on its own, none of it compared to what came next. In October 2025, a team at the Freie Universität Berlin, led by researcher Nozer Khawaja, and working with longtime Cassini instrument scientist Frank Postberg, went back and reanalyzed data from a specific 2008 Enceladus flyby known as E5. That encounter had been faster and closer than nearly any other pass. Cassini made of the moon, and the ice grains it collected were only minutes old, ejected almost directly from the ocean below, rather than having drifted for months or years through Saturn's rings, where radiation gradually breaks down organic material. Using analytical techniques that didn't exist during Cassini's active years, Khawaja's team identified molecular fragments never detected before, aliphatic and cyclic esters, alkenes, ethers, and tentative traces of nitrogen and oxygen-bearing compounds. The findings were published in Nature Astronomy, and the response within the scientific community was immediate. Frank Postberg put it plainly, these molecules found in freshly ejected material show that the complex organics Cassini had detected years earlier in Saturn's E-ring weren't simply produced by long exposure to space radiation. They're readily available inside Enceladus' ocean right now. That distinction is significant. It means whatever is happening beneath that ice and some ancient frozen chemical left over, its active chemistry happening today. 900 million miles away, generating molecular complexity. Nobody expected to find that far from the sun. Consider what has to be true for that chemistry to occur at all. For esters, ethers, and nitrogen-bearing compounds to form inside Enceladus at the concentrations. Cassini measured the ocean can't be a simple cold, still reservoir. It needs an energy source. The silica particles found earlier in the mission already hinted at the answer. Grains of that particular size and composition only form when very hot water meets rock at high temperature, which strongly suggests Enceladus has active hydrothermal vents on its seafloor chemically similar to the vents found on Earth's Pacific and Atlantic Ocean floors. Since that kind of life thrives on Earth in total darkness, powered by geology rather than sunlight, the question of whether something similar could exist inside Enceladus moves from speculation to a serious testable hypothesis, one that Cassini's archived data is now driving directly. Earth's own deep-sea vent communities weren't discovered until 1977 by scientists who assumed the ocean floor near volcanic vents would be lifeless, sterilized by heat, crushing pressure, and total darkness. Instead, they found thriving ecosystems, tube worms, taller than a person, blind shrimp, and colonies of bacteria converting chemical energy directly into food. None of it depended on sunlight. That discovery permanently reshaped what scientists consider a habitable environment. And it's the direct reason Enceladus is now taken so seriously as a candidate for life. An ice-covered moon with confirmed hydrothermal vents, a confirmed active ocean, and now confirmed lipid precursor molecules. It's no longer a fringe idea. It may be one of the most promising places to search in the entire solar system. By contrast, a fresh analysis published in September 2025, revisiting measurements collected more than a decade earlier, challenged the long-held assumption that Titan hosts a large, deep subsurface ocean. Whatever is going on inside Titan appears to behave differently than researchers expected, and its internal structure remains far less understood than previously believed. Then there's Mima's a moon so small and visually unremarkable that for most of the mission, scientists barely gave it a second thought. It looks almost like a toy, a plain cratered ball of ice, best known for one giant impact crater that gives it a passing resemblance to a certain fictional space station. It showed no geysers, no plumes, no obvious sign of internal heat or activity. In February 2024, researchers studying subtle irregularities in Mimas' orbit, tiny wobbles. Cassini had recorded years earlier, announced something nobody had predicted. The evidence had been sitting in the orbital mechanics data the entire time, waiting for someone to ask the right question of it. What makes Mimas so unsettling to planetary scientists is exactly how ordinary it looks. Enceladus, at least, had visible geysers as an obvious clue that something was happening beneath the surface. Mimas offered nothing. Its surface is heavily cratered, ancient and geologically quiet, precisely what you'd expect from a small, cold, inert ball of ice with no internal heat source. The discoveries clearly did not. Engineers studying a possible future. Enceladus mission have floated several designs from an orbiter that would repeatedly fly through the plumes with far more sensitive instruments than Cassini ever carried to a lander that would touch down near the south polar fractures and sample fresh material directly at the source, without it having to travel through space and lose delicate organic signatures along the way. The entire field of astrobiology has been reshaped by what Cassini found. Scientists now speak seriously about ocean worlds, distant moons hiding liquid water beneath frozen shells, as high-priority targets in the search for life beyond Earth. Titan, Enceladus, and Mimas were once just theoretical questions. Because of Cassini, they're now backed by measured, published, peer-reviewed evidence, and the papers keep coming. What makes all of this even more remarkable is that Cassini was never designed to search for life. Its instruments were built to measure magnetic fields, chemical compositions, ring structures, and atmospheric dynamics. The toolkit of a generalist explorer sent to study a planet nobody fully understood. It wasn't hunting for cell membrane precursors. It wasn't searching for hidden oceans, and yet buried in its final transmissions. In the 22 death-defying dives through a gap no spacecraft had ever entered, and in a routine 2008 flyby that sat untouched in an archive for 17 years, it found exactly that: molecules that build the walls of living cells, oceans hidden inside moons that looked completely dead from the outside rings, evaporating into their host planet at a measurable rate that gives them a real expiration date and a magnetic field that, by the models we trust for every other planet, shouldn't be able to exist. None of it was what Cassini was sent to find. All of it was quietly present in the data, waiting for scientists to develop the tools and understanding needed to finally see it. Researchers estimate it could take another decade or more to fully mine everything hidden within Cassini's complete dataset.